4.7 Optimization Problems. Optimization problems are a use of calculus in the real world. It is when we want to find the largest and or smallest that a function can be. So we've already saw how to solve one optimization problem when we dealt with the extreme values of a function. We found the largest and the smallest value that a function would take on an interval. So when is it used? Suppose you own a pizza parlor and you wish to maximize profit. You're going to decide how to have the box made in a way to hold the greatest volume and cost the least. So you're going to have to optimize your function. This happens with anything like shampoo bottles and any other item that is in a shaped container. Like with the shampoo bottle, a cylinder is the best to hold a liquid volume, and that's why most of our things that are holding liquid are in some form of a cylinder shape. Now, if you're buying a shampoo bottle that has all these weird shapes on it, you're paying for the bottle, not the actual shampoo inside, because what we would need to do is optimize that function to get the most into the bottle, which is a cylinder. So, a box manufacturer desires to create a box with a surface area of 100 inches squared. What is the maximum size volume that can be formed by bending this material into a box? The box is to be closed with a square base, square top, and rectangular size. So draw a sketch, then write out known formulas and information. So there's our pizza box. The area of the base is x squared because it's a square. The side is x times h. And therefore the total is 2x squared because there's two tops. There's a top and a bottom, so 2x squared, plus 4 sides, 4xh, and we want that to equal 100. So our volume is length times width times height, which is the area of the base times the height. The area of the base is x squared, and the height is h. So since we're trying to maximize the volume, we need to eliminate one of the variables in the equation. So to do so, we're going to solve one equation for one of the variables and then substitute. So 2x squared plus 4xh equals 100. Therefore, h could equal 500 minus x squared divided by 2x with a little algebra. Now substitute this in for the place of h in the volume equation. So volume equals x squared times the height, but in our case that's 50 minus x squared divided by 2x. Therefore, the volume equals 1/2 50x minus x cubed. So find the derivative of the volume equation in order to maximize the volume. So it was 1/2 50 minus 3x squared. So set the volume equal to 0 and solve for x. Now we know that x is plus or minus the square root of 50 divided by 3. So plug this x value into the volume equation and simplify. So the volume equals 68.04138. Now we're going to use the second derivative test to verify that this is the maximum value. So find the second derivative, 1/2 minus 6x, 1/2 times the negative 6x. Therefore, the second derivative is negative, which implies we have a maximum at this point. That is a little bit summary of the maximum values. That is also what is similar to our odd and even functions and our symmetry, and some other topics we have previously covered in this class. Therefore, the maximum volume of the box is approximately 68 inches cubed. So, steps in solving the problems. First, you need to read the problem. Then draw a diagram. Then introduce notation. So in the previous problem, we introduced x as being the side length and h as being the height, or anything like that. Then express q in terms of some other symbols where we found the area and the volume formulas. Then we eliminated all but one variable, so that then we can take the derivative, and when we take the derivative, we can find the maximum, and then we can check that by using the absolute maximum or minimum value of f. So a farmer has 24 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? Step 1, read. Step 2, draw. Here I am drawing multiple figures to get the feeling of the problem. So these are all different things that could happen. But in order to find the maximum problem, I'm going to plug variables in for these. So a specific diagram with notation from step 3. Then, here is step 3, introduce that notation. So you could kind of do those backwards if you want to, it depends. X equals 8, and the area equals x times y. And the perimeter, we have two x's and a y, so 2x plus y. So I know that my perimeter is 2400, so I can say 2400 equals 2x plus y. Now solve for y and get y to equal 2400 minus 2x. Step 4, now plug in for y in the first problem, so we have only one variable. X area equals x times what we found y to be, 2400 minus 2x, which gives us 2400x minus 2x squared. Next step, take the derivative. So we get 24x minus 2x squared, and the derivative of that is 2400. That should be 2400x minus 2x squared. So the derivative of that is 2400 minus 4x. Now find the critical numbers. 2400 minus 4x, therefore, equals 0. So I can solve for x, and I get x to be 600. Now I'm going to plug it in. For an area of 600, I get 720,000. And that is the maximum area. Here's another application problem. Find the point on the line 6x plus y equals 9 that is closest to the point negative 3, 1. So y equals 9 minus 6x. So we are looking to maximize the distance between a point on the line given x 9 minus 6x and negative 3, 1. So here we can use the distance formula. And when we use the distance formula, we are getting rid of our y's and replacing them with the 9 minus 6x. So we're down to 1 point. Now, you can use your calculator to do this. Enter the distance function into your calculator and store it with stow greater than key as y1 of x. Then you can select solve from the F2 algebra menu and differentiate option 1 in the F3 calculus menu, and you will need to type in the rest as shown in purple italics. So you work on this personally because you know at certain points in the test it will be non-calculator active. So this is just a little bit of information for you to practice on your own for the calculator active portion of the test. So when you do this, you should get x equals 1.216 rounded to 3 decimals. And then you can calculate the y coordinate using the function rule. So then you just plug it in and you get 1.703. What about another example? Find the area of the largest rectangle that can be inscribed in a semicircle of radius r. Step 1, read the problem, done. Step 2, draw a picture. So I have a picture over here to the right where my radius is r and I'm in a semicircle. Now I've decided to use an angle because I know my trig functions, and that seems to be the easiest way to solve this problem. Assign notation and solve. Let's use an angle as a variable, theta. Then the area of the rectangle is 2r cosine theta times r cosine theta. Correct? Because if this is r cosine theta, we need 2 of those, 2r cosine thetas, times our side length, r sine theta. And that is going to equal r squared, times 2 sine theta cosine theta, which equals r squared sine 2 theta. So we know that sine 2 theta has a maximum value of 1, and it occurs when 2 theta equals pi over 2. So when we plug in theta, it has a maximum value of r squared, and it occurs when theta equals pi over 4. And that is it.